Welcome to the MathAcademy.net channel. My name is Bo. And welcome to our series called Mathematics is Hard, or is it? Today we will look at calculus. And welcome to our guest, Alan, who uses deconstruction in his work.
Thank you, Bo.
Alan, what does deconstruction mean?
Well, Bo, deconstruction means what it says: destruction and reconstruction. Deconstruction is used by postmodern skeptical thinking that dates back to the ancient Greek sophists. The sophists warned against patronization, that is hidden in choices that are presented as nature. So to avoid hidden patronization, false nature must be unmasked as choice. And to deconstruct then means to discover alternatives to choices that are presented as nature.
Thank you, Alan. Do you have a short answer to today's question?
The short answer to the question, calculus is hard or is it? Is that calculus is not hard by nature, but by choice. Calculus is made difficult by its missing a link to its root. Reconnecting calculus to its root will make it easy and accessible to all.
And what is the root of calculus?
The root of calculus is adding per numbers. If we add 3 kilograms at $4 per kilograms and 5 kilograms at $6 per kilograms, we get 8 kilograms at a certain price. Here we add the unit numbers 3 and 5 to 8. If also we added the per numbers 4 and 6 to 10, the total price would be 8 times 10, that is, $80, in contradiction to the factual total price, which is 3 times 4 plus 5 times 6, that is, $42.
So per numbers cannot be added?
They can, but to do so, they first must be changed to unit numbers, by multiplying with their kilograms numbers. And multiplying two numbers gives the area of the rectangle having the two numbers as its sides. Thus the total dollar number is found by adding areas, which can also be called integration. So 3 kilograms at $4 per kilograms, and 5 kilograms at $6 per kilograms, gives 3 plus 5 kilograms, at 3 times 4, plus 5 times 6, divided by $8 per kilograms. Thus integration combines multiplication and addition.
But shouldn't calculus begin with differentiation?
On the contrary. Differentiation is just another word for reversed integration. And you must be able to integrate before you can reverse it. As an example, we can ask, 3 kilograms at $4 per kilograms, and 5 kilograms at how many dollar per kilograms, gives 8 kilograms at $7 per kilograms? When integrated, the area 3 times 4, and the area 5 times the unknown, are added to the total area, 8 times 7. So to find the unknown, we must subtract the first area from the total area, before dividing by 5, to get the per number. And where integration combines multiplication and addition, differentiation does the opposite. It combines subtraction and division.
So calculus is just about mixing quantities.
Well, mixing quantities is the main root of calculus. In mixture problems, the different per numbers are constant, which geometrically gives a piecewise constant graph, having the total as the area between the graph and the horizontal baseline, the x-axis. However, with a falling body, its meter per second number, that is its speed, is not constant, but increasing. But the basic question is the same, as for example, 3 seconds at 4 meter per second, increasing to 5 meter per second, gives a total of how many meters? And again the answer is given by the area, onto the per number graph.
But, when changing from 3 to 4 meter per second, then the meter per second number is not constant?
Correct. The per number is not constant, nor is it piecewise constant. It is, however, locally constant, and therefore again the local areas add up to the total area.
What do you mean by locally constant?
Let us give a formal definition of being constant. A number y is globally constant, c, if, for all positive numbers d, the distance between y and c is less than d. Likewise, a variable number y is piecewise constant, c, if an interval radius e exists so that, for all positive numbers d, the distance between y and c is less than d within this radius. Finally, we can interchange e and d and define that a variable number y is locally constant, c, if, for all positive numbers d, an interval radius e exists, so that the distance between y and c is less than d within this radius. In the same way, we can give a formal definition of linearity by saying that the graph of a formula y is f of x is linear, globally, piecewise, or locally, if its change per number, dy over dx, is globally, piecewise, or locally, constant.
It sounds a little abstract.
Formal definitions usually are abstract, together with the names they define, such as continuity and differentiability, instead of constancy and linearity. But what it means is that for any degree of accuracy d, we can find an interval where the distance from y and c is less than the accuracy, that is, y and c will seem to be the same in this interval. This makes a locally constant y graph piecewise constant, so we can add up areas.
But with a high degree of accuracy, there will be extremely many areas to add up.
Indeed there will, unless the areas can be written as changes, for adding up a big number of changes gives one single change, which is the difference between the start number and the end number.
Can you please explain that?
Let us set up a 5-row table with arbitrary numbers in the first column. In the second column we calculate the single changes, and add them in the third column. In the fourth column we calculate the total change from the start number to the actual number. We observe that, since the middle numbers always cancel out, adding any number of single changes gives just one change, the total change, which is the difference between the end number and the start number. We use the old S type for summing up very small changes, dx.
But how can we write an area as a change?
It is straightforward. As an example, let us write the area under the curve h is 2 times x as a change. In the formula y is x squared, a small change in x, dx, will give a small change in y, dy. We can prove that dy is 2 times x times dx. Since a local area under h is h times dx, that is, 2 times x times dx, it can also be written as a change in y, dy. So the total area from x equals 1 to x equals 5 is found by adding up the local changes to one single change, that is calculated as the end number, 5 squared, minus the start number, 1 squared, that is, as 25, minus 1, which is 24.
Okay, Alan, but how can you prove this change formula?
In a rectangle with sides f and g, the area is f times g. If f and g both depend on a third number x, then a small change in x will give small changes in f and in g, called df and dg. And they will give a small change in the area, dA, consisting of 3 parts, df times g, f times dg, and df times dg. So df times dg is the difference between the number dA and the number df times g plus f times dg. This difference can be made arbitrarily small, so locally, dA is df times g plus f times dg. Using dashes for the ratio of changes, we see that f times g dashed gives f dashed times g plus f times g dashed.
Okay, but you talked about the formula y is x squared?
We know that if y is x, then dy over dx is dx over dx, which is 1, so x dashed is 1. Since we can write x squared as x times x, we see that x squared dashed is x dashed times x twice. Thus we have now proved that a small change in x squared is 2 times x times dx.
Then how about the area under, for example, h is x squared?
Since x cubed can be written as x squared times x, we see that x cubed dashed is x squared dashed times x plus x squared times x dashed, that is, 3 times x squared. Thus a local area under x squared can be written as a change in 1/3 x cubed.
So any formula can be written as a change formula?
Well, all formulas have change formulas, but not all can be written as a change formula. If not, we have to add up areas, but with a computer this is no problem.
If differentiation is reversed integration, then reverse differentiation is integration?
It is, but often it is also called differential equations. Thus finding the area under x squared from x equals 1 to x equals 4 can be formulated as a differential equation, asking the question, Given that the local change of the area is x squared times dx, then what is the total change in the area from x equals 1 to x equals 4? Or in other words, find a of 4 by solving the differential equation. A dashed is x squared, given that a of 1 is 0.
Who uses calculus?
Physics and economics both use addition of per numbers. Physics describes the motion of bodies by their speed, measured as meter per second, and by the acceleration, which is the change in speed per second. Economics talks about the rate of change of the price of a commodity, and talks about the relative rate of change, in capitals, or in production, or in a population, and talks about the elasticity, which is the ratio between the relative changes in y and in x, when describing the demand and the supply on a market.
How old is calculus?
Calculus was invented by Newton when asked to explain the motion of the moon. In the 17th century, world trade was about shipping Western silver to India in exchange for pepper and silk. The English robbed Spanish silver ships, returning from South America, but to get to India, they had to navigate by the moon on open sea, to avoid the Portuguese fortification of Africa's coast.
But everybody can see that the moon moves among the stars?
That was what everybody thought, until Newton presented his 4 times no. No, the moon does not move among the stars. As the apple, the moon folds towards the earth, in an eternal orbit, that has the same curvature as the earth. And no, the moon does not follow the Lord's unpredictable will. Its motion can be predicted by a formula for a gravitational force. And no, a force does not give motion, a force gives change in motion. And no, algebra cannot solve change equations. Calculus must be invented to do so.
Alan, you are often quoted for saying that calculus is the 4th and last way of adding. What do you mean by this?
Well, Bo, mathematics is a natural science, about the natural fact many. To deal with many, we count and we add. Once counted, many occurs in 4 different ways, as constant or variable unit numbers or per numbers. So numbers can be added in 4 different ways. Since $3 and $5 add up to 3 plus $5, variable unit numbers are added by plus. Since $3, 5 times add up to 3 times $5, constant unit numbers are added by times. Since 3% 5 times add up to 103% to the power of 5 minus 100%, constant per numbers are added by power. And since the total of 3 seconds at 4 meter per second, increasing to 5 meter per second, is found by adding areas, variable per numbers are added by integration.
Also, you are quoted for saying that calculus should be part of primary school?
Yes, Bo. If 2 totals, 2 3s and 3 4s are added next to each other as 7s, then they are added as areas, which is integration. In this case the total is 2.47s, where we use a decimal point to separate the bundles from the unbundled singles. And if reversed, to find out how many 2s that added to 1 4s gives 2 6s, we first take away the 1 4s, and then count the remaining 2s, which is differentiation.
Why is integration not part of primary school?
Primary school only allows counting in tens, and not counting in icons less than 10. Likewise, it only allows totals to be added on top, and not next to. Instead, preschool should take advantage of the golden learning chances presented by icon counting, and by next to addition, since they allow children to learn linearity, when shifting units, integration, when adding next to, and equations, when reversing addition.
Alan, do you have a conclusion?
Yes, Bo. When calculus is deconstructed, a hidden alternative turns up, addition of per numbers. High school calculus will change from hard to easy, if built upon mixing quantities in middle school, and upon adding next to in primary school. Having once reversed integration, by taking apart and counting up Lego bricks, you never forget differentiation.
Thank you, Alan, for sharing with us your view on calculus. Next time on the mathacademy.net channel we look at preschool mathematics.